Welcome to our talk for Design Automation Conference number 60 in 2023. The topic of our talk is fault injection in native logic and memory computation on neuromorphic hardware. I'm Dr. Jan Moritz Joseph, and this is a work from our team at RWTH Aachen University in Germany, led by Felix Staudigl. Neuromorphic computing is a relatively broad term that summarizes a lot of different approaches to increase compute efficiency. In general, it donates compute methods that are inspired by the human brain. We need them because many AI algorithms especially are limited in terms of power efficiency on today's platforms. One of the core reasons for that is that the von Neumann architecture uses a separated memory and CPU system. So for every piece of information, for every data of your algorithm, you need to get it from the main memory into your compute units and vice versa. And this costs time and, more importantly, also energy. So for AI workloads, we are looking for a more efficient solution, and neuromorphic computing, so a chip that is inspired by the way the human brain works, is one possible solution for that. So you find many different terms. For instance, analog data processing is one way to tackle this, or also spiky neural networks are often used under the term of neuromorphic computing. What we are looking today into is compute-in-memory architectures. So here the idea is that just as in the human brain, you don't have to move the data between the memory and the CPU, but the neurons are statically assigned towards memory addresses and are computed within the memory. So this eliminates those costly data movements here, and in turn we can improve the latency, we can improve the energy efficiency, and also the privacy because your data don't leave the device. There are different ways to use an in-memory compute system. The most general setup that you will find in nearly all of these systems is that you have a crossbar array, so some structure that looks a little bit like this, where you have compute cells as the core compute unit, and then you get data in from one side and you can get data out from the other side. This is something we call analog computing in memory. And so the idea here is that you assign your neurons to a memory cell and then you get the input data in and you compute within your memory cell. This is somewhat inefficient still in terms of conversion from analog to digital and vice versa, and also it has a relatively low fault resistance. So this mode is not always the most efficient that you can get, even though your analog compute in memory operation itself is super efficient. So another mode that was published recently is called logic in memory mode. So it represents an orthogonal approach to the analog computing in memory that is supposed to be less error prone and doesn't require analog and digital conversion. So here the idea is that you do not understand the memory cells as a cell that has a weight value inside for your neuron, but instead you understand this as a status of a logic operation. So for instance, this can be in a high or low resistive value, and this represents a 1 or a 0 in your device. And then what you want to build is essentially some logic operations from this. So you want to say, okay, let's say here is a 1 and here's a 0, and I want to do an AND operation, and I want to write the result into an out cell here. So essentially, you want to do logic in memory, meaning you take the status of two logic cells and you write the resulting status into a third memory cell depending on the logic operations that you are performing. And this is then done column-wise. So in each column you have a vector of binary values. So for instance, of in vector 1 and in vector 2 here. And then you write a vector to the output operation. So what we show here is an XNOR operation. So the idea of the XNOR operation is that this is one of the core operations that you need in binary neural networks, and this is why we take a look at this especially today. So what you have to take home from this slide is what you can do for logic in memory is you have your binary status written into your memory cells, you get the binary status out, and row-wise you do your operation, and column-wise you have vectors on which you can execute the operations in parallel. So the impact of faults, which is the topic of today's talk, for SIM, analog SIM is well understood, but for logic in memory it's not. So this is why we are taking a look at this today. The nice part about this logic in memory is that you can basically do any operation. So there are different families of logic in memory, and you can map it to any logic operations that you want to have. So as I already said, we are taking a look at the resistance state of each of your logic, of your cell. And then you have a high or low resistive state in these cells, and then you can do a logic operations, and then you basically have basic operations inside your logic family, magic or imply. These basic gates, for instance, are an OR gate or an OR gate, and then you can extend these gates towards more effective operations on a larger scale, for instance, to generate an XNOR that we need for binary neural networks. And the nice part is that these logic operations change the state of the memristor, but your data never leave the memory. So this is the most efficient way to do computing in memory. So, as I said, we want to take a look at the impact of faults on these models to use computing in memory with logic. And for this, we are proposing a new simulation flow that we call FLIM. So it's basically a fault injection framework so that you can do a reliability assessment of your logic and memory operations. It consists of two general parts. One is the fault generator, and the second is an inference model where you can actually run your BNN model. So let's first take a look at the fault generator. So for the fault generator, you have to give it different inputs, your injection rate, the type of fault that you want to model, the crossbar model that you are working on, as well as your model for the machine learning algorithm that you want to do. And then we have three parts inside our fault generator. The first is the fault distribution. So this distributes the faults onto the crossbars. Then we have a fault mapping, so you're mapping now your model onto the faulty crossbars, and by that you get individual cells that are affected by certain faults, and then from this we can extract a noise vector. So essentially this then represents a vector that gives you information about which cells are functional and which cells are dysfunctional. So this is what we represent here. So individual cells might be affected by a fault or not, depending on the type of faults, your crossbar size, and the fault model that you have. And then you can take your binary neural network model and you can actually run the inference and then use those faulty pieces of noise vectors to append towards your fault model. And then what you get is essentially your real inference as it would run on your device. So what we take in the inference phase is we take this fault injector module that takes the noise vector that we extracted from our fault generation. We insert it into an extended version of the DAC TensorFlow library, run this through conventional TensorFlow afterwards, and then we can see that this obviously is a really nice dog, right? As you can see, no faults happened here. So there are two different kinds of faults that we can model in our framework. So we can both model permanent and transient faults. So permanent faults are stuck-at faults. Stuck-at faults means one cell is just stuck at a certain value, and this basically limits the lifetime of your device because it's the endurance limit, right? You have used your cell for a certain number of times, and then it's stuck with one value, and that's your lifetime. And then we also have bit flip faults, so these are transient faults. So these can happen due to environmental variations during the lifetime of the device, but they heal themselves after a certain time. So for some time a cell is at the wrong value, and then it goes back to the right value again. So let's first look into the actual fault injection into our BNN model, how this works, because it's a really neat trick that we applied here in FLIM. So what you see on the top is essentially your BNN model, right? Think about it as a convolutional model. You have tensors and you do tensor operations on these, and then at the end, as in any convolutional network, it goes narrower and narrower and you get your classification result easily visualized here. So what we now do is that we can think about this as each of these operations is mapped towards a crossbar array, and then you have some faulty operations inside your crossbar array. So essentially what we want to know is what is the actual outcome that we would get in hardware from each of these layers. So we append a fault matrix here. And so what we do is, and this is shown at the bottom of the graph, we have our kernel, that is a binary kernel, because we are taking a look at binary neural networks. We have to execute an XNOR operation, and then we get an output tensor. So this is just the normal way your DAC/TensorFlow model works. But then we know which of these values has been assigned to which cell inside the mapping phase of our neural network mapping to the logic and memory. And we also know from our fault simulation which of the cells is currently faulty or is not faulty, both during lifetime or as an endurance test. So basically we get masks for this. So we get a bit flip mask and we get a stuck-at mask. So these are the two masks that we apply. So in terms of the bit flip mask, we can say, okay, but these bits will be flipped. And also we can see, okay, but this cell is always stuck at a 1. So we get a relatively easy way of understanding how our errors behave. And then what we finally get out is a faulty tensor. So we do a second operation on our tensor and append those two bar masks. So we get the correct output, including all the errors, to the faulty overall result of your layer in your neural network. And this is really nice because now we can run the whole neural network and see how our device would change the results that we get from computations. Okay, let's take a look at the results. So first we want to take a look at the injection of permanent or transient, meaning dynamic faults that change during the lifetime. So we have three different graphics here. Number one is stacked faults, and then bit flips that are statically injected and bit flips that are dynamically injected. And then on the x-axis you see that the injection rate is increased for the first two ones. So let's explain the first two ones. The third works a little bit different. But on the y-axis you always see the accuracy of your operations. And we are taking just 3 example operations, 2 convolutions and 2 dense layers from a LINET with an MNIST dataset. So what you can see now is if you increase your injection rate, something that might be not super surprising, that your accuracy of your layer is dropped. So this is in terms of something you would expect. If we inject more errors, then your accuracy drops. And then also the combined accuracy for the whole MNIST dataset here drops also quite significant. And you can see that stacked faults are really an issue here. But you can tolerate quite high injection rates, up to 10%, and you still have a single-digit error accuracy drop. For bit flips that are statically injected, it looks a little bit different because here your accuracy drops much faster. So this is really an issue because now you can see that stacked faults are somewhat tolerable, but bit flips are not. And then finally what we have done here is these dynamically injected bit flips, so bit flips that heal themselves after a certain amount of time. So what you can see here is we start with one instance of time, and then we run and run and run the number of XNOR operations. So this is basically a time axis here. And then after 4 operations, your dynamic bit flips have healed themselves partially, depending on the time they need to heal. And then you can see that obviously if you start injecting a lot of faults, your accuracy will be relatively low, but the device can heal itself over time. So we are not injecting new faults to show this healing behavior, but this is a really neat behavior because you can see that these dynamically injected bit flips have the opportunity to change their behavior over time and also change the overall outcome that you can see for your BNN operation over time in a positive way. Okay, so this now shows us this for individual layers here, and yeah, so we can see that some of these operations are independent from the layer, some are not so independent also from the layer. So you can see that there's difference between convolutions and dense layers, but you can also see that the device heals itself over time. What we also wanted to take a look at is the difference between row and fault injection for rows and columns, because if you think about it from the beginning, in the column-wise we had the vectors and row-wise we only had the operations. So you would expect that if a whole vector is faulty in your model, that this has a different output than if just one operation is faulty inside your model. And this is also what we can see here. So on the x-axis here you have the faulty columns. On the y-axis you have the accuracy. We again use the model from before, the BNN on MNIST with LINET as a network architecture. And then you can see that if your number of columns start to increase that are completely faulty, then your accuracy drops relatively sharply and fast. So with even after 3 fully faulted columns, like you can just throw away your model results. But then for the number of affected rows in one crossbar here, it looks a little bit different. So you can just tolerate more of these faulty rows because it's just infecting one operation, but not a whole input or output vector. So you can see that the decline is less severe in this model. So yeah, so this shows you that indeed we have a different effect from the mapping of your crossbar and the way the logic operations work. Another really important concern is the simulation speed, because all these nice results are not really usable if you can just run your whole BNN model at a decent speed and just get the results. So this is an old work, X fault. As you can see, it really took long, even if you accelerated on a GPU. So this was runtime in seconds to the power of 6, so that's really not usable for the whole data set for MNIST, and you can think about it, it's only an MNIST benchmark here, right? It's not, we are not running huge state-of-the-art models. Vanilla Lark here is basically running the model without any fault injections, and you can see there's a huge difference in terms of the state-of-the-art before this work and the vanilla speed that you can achieve. And then FLIM, the work that we are showing here today, is right in the middle, and we are really happy about the results because it's much faster than the X-fault simulation methodology that existed before. It is still slower than Vanilla Lark, but anyways, we're doing a fault simulation, so I think that's okay. It's about 1 order of magnitude slower than Vanilla Lark, but it's many orders of magnitude faster than what we achieved in state-of-the-art before. Okay, and this nice simulation speed can now be leveraged to run this model on the whole ML model, so to see how resilient is the ML model as a whole for faults. So we have tested different ML models here, not only MNIST and LeNet, which is simple, I know. So you can see dense AlexNet and different other XNOR nets for the binary input, and then again on the X-ray axis you see the injection rate of different faults. So we have on the top side the bit flip that is statically injected, and on the bottom the stacked faults. And then again here you can see bit flips are much more resilient, or the models are much more resilient towards bit flips, because you can see that the injection rate is here between 0 and 10%, and your accuracy drops significantly, but it's on a single-digit axis here, while here on the stacked faults, you see we are below 1% and already have a trashed accuracy. So this is really severe, that your performance drops significantly. And then you can also see that different models behave differently. Some are more resilient towards these faults. For instance, the ResNet model here is much more resilient. Other models are not, but this is something you can now for the first time fast and efficiently evaluate based on the framework we are presenting here. Okay, so to conclude, we have proposed FLIM, a new methodology, so that you can evaluate the impact of faults in the field related towards emerging memory applications. You can run both statically and dynamically injected flips, so we can have bit flips and we can have stacked faults associated with your memory. The performance is much faster than what we have seen before in similar frameworks, so we are outperforming the X-fault framework, for instance, by 4 orders of magnitude, and we are within range of just native execution of your BNN model. And as future work, we are going to extend this so that we can have more complex applications on the higher level, because this was only done for binary neural networks, and it's most interesting to extend this to non-binary neural networks as well. Thank you for your kind attention, and have a nice day.